Welcome viewers at another Tech Talk here at bestofhighend.com. In our podcast studio today, still Bruno Putzeys. Again, welcome Bruno.
Thank you for having me.
In this episode, we'll be talking about Purifi products, mainly in this episode about the Eigentakt amplifiers. So Bruno, we have amplifiers and we have speaker drivers. Let's talk about the amplifiers. It's called the Eigentakt amplifiers. Was there a need to come up with this kind of amplification? Where did that come from?
It actually came quite naturally because we, as you might recall, we initially wanted to do a digital speaker control algorithm that would then be packaged in a DSP controlled power amplifier. But as soon as we decided to do drivers, then that sort of meant that the whole amplifier question was up in the air again, and by that time Encore was I think 6 or 7 years old, and I did feel that the time was ripe to have some to try some new ideas, and that became the Eigentakt amplifier.
Mm-hmm. What's so revolutionary about these designs?
Well, I've got to correct you there. In the case of amplifiers, nothing is revolutionary. It's only evolutionary.
Okay.
Because there is really a clear line throughout my amplifier, starting from UCD all the way to Eigentakt. The reason being that, well, like several other people, I'd quickly discovered that so-called self-oscillating amplifiers, so amplifiers that don't have an explicit oscillator followed by a PWM modulator, but ones where the feedback loop itself causes the amplifier to oscillate. Those tended to be much more robust in terms of audio performance, and you could get more loop gain out of a similar circuit if it's self-oscillating, I worked that out in practice during my Philips days, but not fully understanding why. It's always been sort of in the back of my head as an annoying, nagging little mystery, why that should be the case. And it's really only when I started on Eigentakt that the penny dropped. So the biggest change between Encore and Eigentakt is not so much the actual circuit. Of course, the circuit, there are differences in the circuit. We've even patented those differences, but fundamentally, it was the fact that I found a treatment for self-oscillating pulse width modulation or a mathematical model for pulse width modulation at duty cycles other than 50%. That's very technical, but it was actually very, very fundamental. The thing is, a Class D amplifier really only ever responds to whatever is happening inside in terms of input signal or in terms of control signal at the exact moment that it switches. So it is the only thing you can do is the output stage produces a square wave, and you can only shift the moments that when the output stage changes state. It's the only thing you can do, meaning that between those two states, it doesn't respond at all. If there's anything you try to do between now and the next switching transition, the only thing that can happen is that you influence that next switching transition as a result, and that means that a Class D amplifier, even though a Class D amplifier like mine is fundamentally, completely, entirely analog, it is a sampling system. So there is. It's kind of natural to look then at a Class D amplifier, knowing that it is a sampler inside a feedback loop, to treat it same as you would treat a sigma delta modulator in an A to D converter. and that's as fine as it goes, except that as soon as you start modulating the amplifier away from idle, for instance, you start amplifying a large positive signal, then the amplifier will spend quite a long time sort of in the high state and a fairly short time in the low state, and back high. In other words, the moments when the amplifier samples the signal is not just now and then a microsecond later and then another microsecond later. No, what you get is now, and then it's 1.5 microsecond later, and then it's half a microsecond later, and then it's 1.5, and then it's a half. So this it's called non-uniform sampling, and until then there was absolutely no usable mathematical treatment for that. In actual fact, there were in those days still relatively few people who realized that a uniformly sampled Class D amplifier should simply be treated as a sample system, and that you could use what's called the impulse invariance transform to get from your continuous time loop to a sampled equivalent of that. Let alone that anyone would have known how to deal with it if the sampling periods are no longer constant. And it was really figuring that out, how to analyze the loop in these other circumstances, that allowed me to then optimize the parameters of the loop such that it would remain stable to up to clip, whilst still having a large amount of loop gain under normal operation.
And how does this translate to audible performance?
Well, in the end, it translates into me being able to increase loop gain by more than 20 dB. Currently loop gain on this little baby is about 80 dB all across the entire audio band, which is, well, rather astronomical. But what it translates into is that you no longer hear any measured distortion drops, meaning that you no longer have any impact on the output signal of either the output stage or the power supply or the output chokes or the output capacitors. And actually, the output chokes, it turns out, in terms of distortion, are pretty evil. Distortion created by a ferrite inductor is not very large, but it's extraordinarily complicated. We put a little animated measurement. It's an actual measurement, by the way, but a little animation on the Purifi website, where you can see just how impossibly intricate that the distortion is that's created inside a magnetic material, and that distortion, it turns out, is actually responsible for the most recognizable Class D characteristic. So most people don't notice, but a couple of people kept coming back saying, like, I hear some sort of some sort of a grit or hash or something, or a kind of veil hanging over the stereo image, and it's something that I only hear with Class D amplifiers and with no other technology, and so on. And for a long while, I sort of dismissed that, until I actually figured out, whilst looking at loudspeaker drivers, not at the ferrite code, but whilst looking at loudspeaker drivers, just what magnetic material is capable of distortion-wise. And then, of course, the penny dropped. And you said, okay, so because the type of distortion that happens in magnetic materials is correlated not only with the signal that you hear that is passing through the amplifier now, but also the signal that has passed through the amplifier before, it kind of evades the usual masking effect. So normally speaking, if you have a simple nonlinearity like say a single triode in an open loop situation, that can have pretty high, pretty large amount of distortion. But it's distortion that is only present at the exact same time when the signal is present that causes that distortion. And then there's something called psychoacoustical masking. It's the same thing that makes MP3 and AAC codecs work. Is the fact that your ears simply cannot resolve small signals at the same time that a large one is present. And all of the tests that had so far been done in more academic circumstances and at the AES and so on, that trying to establish just what percentage of distortion is audible. They all use that kind of what we call memory-less distortion, and they all came up with staggering percentages that you had to have in terms of distortion before people started picking it up. And that of course, that observation flies in the face of what we found in amplifiers. But it's basically clinched by the fact that the distortion that you get in ferrite is not memoryless, and it actually happens. So it's semi-correlated with the signal, but not fully correlated, and that causes that gritty veil. But fortunately, shall I say, unsurprisingly to me, but surprisingly to a lot of other people, feedback is perfectly capable of dealing with that, with this kind of distortion, which should be obvious to anyone understanding noise shaping. That this is a noise shaper basically, and it just means that it can remove that distortion inside inside the audio band, and as a result, the sort of that hash disappears, and you're left with a much more natural, much more flowing sound.
Mm-hmm. Well, talking about specs, it's really impeccable. It has a power output that is quite high. If you look at distortion, it's way down, it's way low. How would you describe the overall sound of an Eigentakt amplifier if you compare that with more traditional approaches? Basically, for me, it's kind of warm and organic, sort of directly appealing to your musical senses. The amplifier itself just doesn't draw any attention to itself at all, basically. But if you then compare that to other amplifiers, then the amplifier sounds comparatively warm compared to other amplifiers as a result. Yeah. How long did it actually take for you to develop this module, or the Eigentakt modules?
The Eigentakt circuit was designed in a couple of in a couple of stages, and we took our time. I think for most people, most people would say it was quick because it was done in a year, I think. But it was still done in stages. So first the insight was that you could rearrange the control circuit in such a way that it opened up, that it made it possible to achieve different sort of frequency transfers that for instance, the Encore circuit couldn't, and that gave that, and then came the moment where I got this sampling model, that I got that done, and then I could use a sampling model inside an optimizer, which is basically a MATLAB script that twiddles the component values of the loop, and then predicts what the amplifier would do if a loop with those component values were being used with it, and so at that point you no longer need to calculate components. You just let this thing rip for a quarter of an hour or so, and it'll spit out a list of components that will provide you with the highest possible loop gain for a given maximum switching frequency and for a given maximum operating duty cycle.
Mm-hmm. Would you call this technology superior in regard to, let's say, Class AB, Class A, or even valve amplifiers?
Fundamentally, when you decide to do Class D amplifiers, you do that because you want the amplifier to be efficient and compact. You don't want to waste power, basically. After you've done that, a Class D amplifier will essentially try and do anything but amplify music. You have to tame the beast. Let's say doing a Class A amplifier with unmeasurably low distortion would actually be a walk in the park compared to this. Because a Class A amplifier has a much higher bandwidth to work with. It's much easier to design to achieve a certain loop gain. Not that anyone seems to be trying, but let's say with this knowledge under my belt, I would know how to attack the design of a linear amplifier, and it would be a lot simpler. So yeah, so it is definitely not true that Class D is inherently better for audio quality. It is possibly the most unwieldy way thinkable of amplifying a signal. But well, no one's waiting for a better diesel engine, are they? So. So for me, the challenge has not been to design lovely sounding amplifiers because they're Class D. No, my challenge has been designing lovely sounding amplifiers in spite of the fact that they're Class D.
Okay. Well, you described the sound as being warm and natural, and obviously kind of getting a feel like there is no amplifier. Mm-hmm. But that seemed to be the end goal here, in terms of
as I would hope would be the aim for any amplifier designer. Mm-hmm. But so far there are not that many, especially high-end amplifiers out there that seem to have this ethos behind them. There are a couple, and so there are a couple of those big beastie Class A amplifiers with fantastically good measured specifications. And big surprise, they sound very much alike.
Mm-hmm. Well, I have had the pleasure of listening to a lot of these modules and Eigentakt amplifiers on a lot of speakers, and kind of things that always reoccur is like they have impeccable control of the speakers. For instance, the bass, the low frequencies are controlled, very punchy. There is a resolution that's there, and if the speaker allows it, the high frequencies are indeed very organic, very open. It's just, yeah, like you described, it's warm, it's organic, like it's just a pure reproduction of musical intent. Mm-hmm. And yeah. That's for any audiophile or music lover. Even more, it's the thing to strive for.
It should absolutely be, because this is kind of what gets my goat and high end is that people think it's all right to mess with the sound, but I think in a studio environment where actual artists are working and where they are doing where they are producing something, anything is allowed. They can use any kind of microphone, and as far as I'm concerned, they can use any kind of effects, gear, distortion, anything they like, so long as they know that is precisely what they are trying to achieve, what they are trying to bring to their listener. And then that thing is printed as a master and distributed over streaming or as or maybe a physical format. And at that point, people should keep their hands off it, because you definitely do want to hear what the artist was trying to do. Because someone can make a system that sort of, it sounds very complimentary, very pleasant with certain music, certain recordings, and so on. But what those systems are doing is they're just putting some sort of a sonic sauce over the
adding cream and sugar.
Exactly. But think about this: a chef who adds the exact same sauce to any dish wouldn't remain a chef for very long, would they?
No, not at all. Well, this was an interesting talk, viewers, on the Eigentakt products, the amplifier products from Purifi. Glad to have Bruno talk all about this. Glad you could join this episode. In the next one, we'll be talking about the Purifi drivers. Hope to see you then. Bye for now.